Great. So in the last chunk, we were getting used to hidden Markov models in the case where the hidden state took one of k discrete values. And here I'm going to ask you a couple of questions about this model in order to relate them to other models and to think about the sorts of statistical properties that they have and what data they're good at capturing. So in order to do that, I want us to actually return to one of the models we looked at in the last video, where our hidden state can take one of k values. I'm explicitly writing down our initial state probabilities here for our Markov chain on X. That's initial state probabilities are just these pi k's, and our transition matrix is governing our dynamics here, our transition probabilities of our latent variable X. And we're going to assume that our observed data are generated according to an emission distribution, which is a Gaussian whose mean and covariance depends on the state which the latent variable is in. So you look at which state your latent variable is in, and you look up your appropriate mean and covariance of the Gaussian in order to generate your Y's. And the question I want us to get us started with is thinking about what type of distribution is the distribution over the initial observed state, P of Y1. So we know that the distribution over the initial latent state is just given by these pi k's. But I want us to think a little bit about what the distribution over the initial observed variable is here. So pause the video, think about that for 30 seconds, and then we'll talk through the solution here. Great. So I hope you did pause things, and let's go through and calculate this. So here I'm going to use, again, the sum and the product rules. Almost every question in this course, or with high probability, a question posed in this course requires the sum and the product rules to solve those questions. And here we're going to do the same thing. So what have I done? Well, I'm going to write down the joint distribution over x1 and y1. That's this thing. And we know that by the sum rule, if we sum over k here, sum over all the possible settings that the latent variable can take, that's going to be the marginal distribution over y1. Okay. And then I've just used the product rule to split this guy, this joint distribution, into the probability of x times the probability of y given x. And the reason why I'm doing that is I can now go and plug in the initial state probabilities in here and the emission distribution in here. Great. So when I do that, when I make that substitution, I just get this thing. So the distribution over y1 is these pi's times these Gaussian distributions. And hopefully you recognize this from the clustering lectures. This thing is a mixture of Gaussians model, where the mixture components are given by the initial state probabilities for the Markov chain, and the components themselves, the Gaussian components themselves, are just the components that come from the emission distribution. So hopefully this is straightforward. Essentially, it's saying if you ignore all subsequent entries in the time series and just focus on the first element of the time series, and it's particularly the first observed element, that's just going to be a little mixture of Gaussians model. Great. Okay, so that's one connection between this model and previous things we've looked at. So question number 2 is the one that I really wanted us to focus on, which is what distribution does the marginal distribution over the observed variable converge to after a long time? So you should think of this as relating to concepts like the invariant or stationary distribution that we've covered before. So I want us to think about running one of these HMMs for a really, really long time period, and then looking at the marginal distribution of the observed variables at the end of running this for a long time, and asking what kind of distribution this is. Great. Okay, so let's give you 30 seconds or so to go away and compute that, and we'll then sort of go through the answer. Good. Okay, so here's the way I would reason about this. So first off, let's focus on the latent chain up here. We've considered these Markov models before, and we've argued that in the case of discrete hidden state Markov models, when you run them for a long time, they should obey this property that the stationary distribution should be recovered by taking the stationary distribution and passing it through the transition matrix. So this is saying that, if you take the distribution at the previous time step, push it through the probabilistic dynamics, you should get the stationary distribution, the same stationary distribution at the next time step. And we said that this was an eigenvector equation, whereby you can compute the stationary distribution by forming the eigenvector eigenvalue decomposition of the transition matrix and look for the eigenvectors with associated eigenvalue 1. Good. Okay, so that's first realization. And the second realization is that this calculation that we did up here in the previous question can be replicated for any time point on the chain. I can always apply the sum and the product rule to say that the marginal distribution over yt is equal to the marginal distribution over xt multiplied by yt given xt, and then summing over the latent variable values here. So this is just, again, applying the sum and the product rule in exactly the same way, but rather than using index 1 here, I have just used index t. The same rule has to apply. Okay, so that's sort of realization number 2. So now I can put these two sort of facts together. And what I'm going to do is I'm going to consider taking the limit as t tends to infinity of this equation. And then we can substitute in, we know for that, in that case, the px infinity equals k is equal to pi k infinity. That's the definition of this thing. The marginal distribution after we've run for an infinitely long time is equal to pi k infinity. So I can substitute this thing in here, and the other term in here is easy. The probability of yt given xt is equal to k. Well, that's exactly the same as this distribution up here, because it's plugging in this thing into the same expression. So when I do that, we can say that this thing limits to, again, a mixture of Gaussians model, where the probability of coming from each one of the Gaussians is given by the invariant distribution of the latent first order Markov model. And the components are the same components that we had before. There's the components from the emission distribution. So actually at any particular time point, we can view this as a mixture of Gaussians model. In the limit, when we look at the stationary distribution, but actually any intermediate time point as well, you can view this as a mixture of Gaussians model marginally at any time point, where the mixing proportions depend on the dynamics of the first order Markov model, the bigram model, which is specifying the distribution over the x's. And in general, you can think of this as a temporal generalization of the mixture of Gaussians clustering model. It is, from this perspective, laying down mixture of Gaussians at every distribution, and the new element, every time point. The new element this is introduced is dependencies through time. So the bigram model up here could encode things like persistence of cluster membership. So if we go back to the previous examples here, if we go back to the example we met in the last video trunk, here the cluster membership can be viewed as being persistent in time. You are tending to belong in the same cluster over many time steps, with occasional switches from one cluster to another. And that's because this transition matrix here tended to put you into the state you were in before with 90% probability and 10% the time you switched. So you can think of this particular hidden Markov model where we've got continuous observed states and discrete hidden states as a generalization of the Gaussian mixture models, where there's dynamic cluster assignments, and the dynamics in those cluster assignments is governed by the transition matrix T.